types of power dissipation which we would come across while dealing any kind of CMOS designs or CMOS structures. What is the main use and why do we need to study about power dissipation is the first thing which we are supposed to understand. Before knowing what is the main use and why we are supposed to study, it's like useless to study this concept. First, the main thing is that why we are supposed to study power dissipation is if the dissipation of the power which increases, it means here the dissipation means we are talking about releasing of the heat. When a large number of millions of transistors are working continuously almost at the same time, then definitely what happens is that due to the rigorous operation of the circuit devices, it releases some heat. The heat is being generated. The heat is being generated. That heat is generated will cause, if the heat which is generated is very huge, it may even cause the device to get heated up, and that even malfunction the operation of the device. So that's why this power dissipation is very important. We should take care of the power dissipation such a way that the devices which are working should not produce more amount of heat, so that the device will be maintaining some ambient temperature where it will be somewhere like cooler in nature. Because of that thing, again, many techniques has come up in order to deal the power dissipation. Like one of the technique is like in order to reduce this power dissipation, one of the technique is that they're right now they're using for the past decade, they're using sleep transistors. Sleep transistors are the transistors which will be turned off whenever that particular transistor is not working. It means that it will not, the power will not be switched to that particular transistor whenever it is not working. Means it will not be consuming the power whenever it's not consuming the power. Definitely, it means I'm not talking in, it will not totally consume the power, but it will not be releasing any kind of heat. Since it is not working, it will not be releasing any kind of heat. So these kind of transistors will be used in order to reduce the power dissipation. So that is one of the technique which is right now mostly a huge amount of research is going on this sleep transistors. So now let us enter into this lecture of power dissipation in CMOS inverter. The power dissipation in CMOS inverter is mainly given by P is equal to VDD into IDC. That's a DC is nothing else but it's a current across drain and this one of the particular terminals. It's like a DC current, and again VDD is a supply voltage. So ultimately it's a basic formula. P is equal to VI. P is equal to VI, where our V is nothing else but the main supply, which is VDD power supply, and IDC is the current which is drawn from the power supply. Since it is drawing the direct current, we can call it as an IDC. So now here in the CMOS inverter, the power dissipation is caused mainly due to various factors. There are like different factors depending upon their categories, and these different factors can also be categorized into different types of power dissipations. So now in this particular concept, we'll try to see different kinds of power dissipations. The first one is called as a static power dissipation. When we come to the static power dissipation, static means we know it's like an immovable. The charges will be completely immovable, like it's a power dissipation which takes place whenever the system is static. So the static power dissipation is mainly due to the leakage current which is drawn from the power supply. So this power dissipation happens mainly due to the leakage current which is drawn from the power supply. Then the second kind of power dissipation is dynamic power dissipation. The dynamic power dissipation is mainly due to the switching of the transistors. Whenever the transistor is switching from high state to low state or low state to high state, during that time, due to the switching transient current and charging and discharging of the load capacitance, this power dissipation will be taking place. Whenever a element of a device, it can be a transistor, it can be a resistor such as a pseudo resistor, it can be a capacitor or any kind of element. Whenever it is switching, then definitely a power dissipation takes place. Why? Because switching means it's undergoing some kind of work. If it is undergoing some kind of work, definitely a heat is been produced due to work whenever the work is been done. That's nothing else but again you might have studied in your physics regarding the Joule's law. Joule's law, regarding that Joule's law, we will be studying about that how the heat is produced with respect to work whenever work is been done. So whenever any kind of switching takes place, due to the switching of the any element in the device, a power dissipation takes place. That's a heat has been released. Dissipation means heat released. Whenever a heat has been released, that kind of heat released is called as a dynamic power dissipation. And here in the CMOS technology or CMOS kind of designs, you should always try to understand about the formula about power dissipation. The basic formula for the power dissipation will be P is equal to alpha times CV square F. So this is a basic formula which is mainly depending upon P is equal to alpha times alpha can be approximated to half 0.5 depending upon the technology. So it is alpha times of CV square F, where C is the capacitive load and V is the voltage, and again F is the frequency at which a signal has been passing. So that's a basic formula, and this is a general formula regarding the power dissipation. P is equal to V into I. Now let us see in detail about all these different types of power dissipations. The first one is called as a static power dissipation. Static power dissipation is also known as a steady state power dissipation. Steady state because it's not in the working state, so our entire system will be steady. In the steady state power dissipation, and the static power dissipation is given as P static equal to I static into VDD. VDD, you can see now it's the current is static because of the static nature of the charges. So we call it as a static current, and P is equal to V into I, the same formula, but it is in terms of static, I static into VDD, where I static is nothing else but it's a current flowing from supply to ground in the absence of switching. Whenever the system is not switching, then if any kind of current is flowing from supply voltage to ground, we call that kind of current as a static current. The static power dissipation the static power dissipation is due to leakage current which is flowing from the reverse biased junctions of the transistor. This happens mainly due to the reverse biased junction of the transistor. You might have studied about the PN junction diodes and everything. Whenever the PN junction enters into reverse bias, definitely there will be some kind of leakage currents taking place. That leakage currents only we are talking here. When you talk about a transistor is nothing else but it's a combination of two types of diodes. So that's why a term has come here, the reverse bias nature of the junction diodes. So junctions, because of the reverse biasing of the junctions of the transistor, this static power dissipation takes place. The leakage current per unit drain are typically, this is an important objective regarding the static power. It's the leakage current for the static range will be from 10 pico amperes per micrometer square to 100 pico amperes per micrometer square at the room temperature. And in the same way, if I talk about regarding the leakage current at the junctions, this leakage current at the junction is also mainly due to the thermally generated carriers. We know that if a leakage current is taking place, means definitely due to some temperature, increase in temperature, there will be some kind of carriers which are moving. That's the charges which are moving. So even because of that one also, the junction leakage current takes place, which we have studied already. This has been studied in the basics of what is meant by PN junction diodes. These charge carriers increase with the increase in temperature. If the temperature increases, definitely charge carriers also increase. Why? Because the main production unit of this charge carriers is mainly because of the temperature. If the temperature is increased, definitely what happens? The charge carriers also increase. Both are directly proportional to each other. So now the power dissipation, which increases with increase in package density. Yeah, this is a very important point. The power dissipation increases with the increase in package density or number of devices. Whenever the number of devices on a chip increases, definitely what happens? The load of the operation of the chip also increases, because it needs to supply more amount of power. Whenever it's supplying more amount of power, definitely what happens? All the transistors will be working at the same moment of time. Then definitely what happens? The density of the devices have been increased on a chip, and if all the transistors are working at the same time, then definitely it will be consuming the power. Due to the continuous working nature of the devices, the dissipation, the heat releasing also takes place. So that's why the power dissipation will increase with the increase in number of devices on a chip. And this formula, the formula for the static power dissipation with respect to number of devices is given as P total static is equal to summation of all the n number of devices into I static into VDD. So this is regarding what is meant by static power dissipation. Let us see now dynamic power dissipation. During the switching of transistors, we have seen that dynamic power dissipation is a dissipation which takes place during the switching of transistors. Whenever all these transistors or elements of the device are switching, definitely what happens, a power leakage takes place, and that current leakages are in fact are liable for this production of this particular power dissipation. During the switching of transistors, current pulses of small durations are produced. Because small durations have been produced, current pulses means leakage currents are produced here, and also due to the switching of the load capacitance, which is connected at the output. How does the switching of load capacitance takes place? Here, the switching of load capacitance means here we are talking about the charging and discharging of a capacitor. Whenever the capacitor is charging and discharging, even during that time, some amount of leakage of current takes place, gets charged through the PMOS transistor, and its voltage rises from 0 to VDD, and also draws energy from the power supply. So during this kind of switching times, what happens? The leakage current takes place, and that leakage current also yields the dissipation in the circuit. That kind of dissipation is also called as a dynamic power dissipation. If a capacitive load increases, its charge and discharging time also increases. Whenever a capacitive load, it means now if I'm trying to use a 5 femtofarad of a capacitor, since the capacitor is very slow, since the output capacitance is very slow, then what happens? The power dissipation will be minimized. Because of the smaller amount of capacitance, the power dissipation will be less. Why? Because it can charge very fastly and it can even discharge very fastly. But when you are trying to use a large capacitor at the output, I'm talking like it's like a microfarad or millifarad capacitors at the output, depending upon the technology, then because of the huge amount of space between the two terminals of the capacitor, it can store a huge amount of charges on the plate 1 and plate 2. Since it has got a huge capacity to store large amount of charge, the time taken for the charging also will be more. And during this time taken, due to this large amount of time, the discharging time and the charging time will become more. And because of this discharging and charging, there will be some kind of leakage currents taking place, and that leakage current also increases due to the increase in CL. Whenever the CL is more, whenever the load capacitance is more, you can say that the power dissipation is more. If the CL is less, the power dissipation will be less. Whenever the load capacitance, CL means load capacitor. Whenever the load capacitor increases, its charge and discharging dominates the current drawn from the power supply. Means again, the leakage current also increases. That increases the power dissipation. If I talk for the square wave input of frequency of FP, so this is the formula which I told just now. The dynamic power dissipation during the switching is given by P dynamic equal to alpha times CV square F. CV square F. Alpha, it is depending upon the technology, so we have not mentioned here. Approximately, it will be from 0 to 0.5, depending upon the technology. In fact, in some of the textbooks, they might even write it as 0.5 CV square F or else half CV square F. But the formula for the dynamic power dissipation will be P dynamic equal to CV square F into alpha. That alpha is nothing else but depending upon the technology. It can be, for example, as of now, you can take it as 0.5, which is even it will be given in your textbook, which you're referring to as per your syllabus. So this is a dynamic power dissipation, that is P equal to CV square F, where F is the frequency, V is the input voltage, that is a VDD, and C is nothing else but it depends upon your capacitive load. The next kind of power dissipation. The next kind of power dissipation here is, it's a short circuit power dissipation. See here, what do you mean by short circuit? Here the short circuit means whenever a inverter is switching, during the switching from logic 0 to logic 1 state, definitely what happens is that for some smallest interval of time, for a very small interval of time, both the transistors will be in on state. You can, it's like it's like for a fraction of seconds, for a very fraction of seconds, this particular transistor, if I talk about with respect to inverter, both the PMOS and NMOS will be in on state. Whenever both the PMOS and NMOS are in on state, means both are turned on. If both PMOS and NMOS are turned on, means a channel is formed between terminals of PMOS and terminals of NMOS. You can see that if you imagine that particular structure now, right from the VDD to ground, a complete channel is formed. A path has been created. Whenever a complete path has been created, there is an there is a way for this current to discharge. That is a discharging of the voltage takes place right from the VDD to ground. This kind of discharging, because of this, both the transistors are turned on for a very fraction of seconds of time. We call that kind of leakage of current as a short circuit current. This happens very actually it happens for a very smaller amount of time, and that is called as a short circuit power dissipation. It indicates that power dissipation due to the short circuit current in an unloaded inverter. In an unloaded inverter means what? Whenever both this PMOS and NMOS are turned on, they right from VDD to ground, a complete path has been created. During this path, a channel has been created, so a direct flow of current takes place from VDD to ground. That is called as a short circuit nature. So during the short circuit nature, a power dissipation takes place, and that kind of power dissipation is called short circuit power dissipation. And it has been given by alpha, that's power dissipation, short circuit is equal to K times K over 12.
Excuse me, sir.
Yeah, please no.
Sir, once explain again, sir. Short circuit power dissipation.
See, Henry, in the short circuit power dissipation, what happens is that these are my two transistors which are connected like this. One is a PMOS and other one is a NMOS. Now here in the short circuit current, this is my inverter. We are talking with respect to an inverter, this concept. So I have drawn here inverter. This is the VDD. And this is a ground terminal, which is of value 0 volts. So the VDD depends upon the technology. So I'm not mentioning the voltage of the VDD. It can be right from 5 volts to 0. Actually, now they are using like 1 volt or 0.9 volts. So now see, in the short circuit current, what happens is that whenever you supply some input voltage over here, whenever you supply some input voltage means what? You're trying to give some input at the gates of the two transistor. Whenever you're trying to give voltage at the input voltage at the gates of two transistor, definitely whenever this input is switching from one phase to another phase, means from 0 logic to high logic or from high logic to 0 logic, in between this switching time of 0 to 1 or 1 to 0, for smallest amount of time, for small fraction amount of time, a channel has been created between the two transistors. Means both will be on. For small fraction amount of time, both the transistors will be on. Whenever it is on means a channel has been created. If a channel has been created, what happens? You can imagine now here, this particular circuit, right from top to bottom, right from the VDD to ground, it looks like a single pipeline. A kind of pipeline structure has been created here. There is a passage for the current to flow from VDD to ground. So whenever a channel is directly created right from VDD to ground, what happens? Definitely a charge leakage takes place, a current leakage takes place, and this kind of condition we call it as an short circuit conditions. So whenever a short circuit condition takes place, a current will be leaking from high supply voltage to low supply voltage, and that kind of current leakages we call it as short circuit current leakages. And whenever this kind of leakages takes place, a heat is been created, heat is been released over here, and that kind of heat released is called as a power dissipation. So the short circuit power dissipation is nothing else but this concept. And this formula for the short circuit power dissipation is been given as by P short circuit is equal to K by 12, K over 12 into VDD minus VT, that is the threshold voltage, VDD minus threshold voltage into T times of RF. RF is nothing else but we are talking about the rise time of the input wave, where TP is nothing else but it's the period of the wave. So
what is unloaded inverter, sir?
what now?
Unloaded inverter, sir. What is unloaded inverter?
Unloaded inverter means you're not loading any kind of input. Means you're not exactly giving the input between that logic 1 and logic 0. You're not exactly making a transistor to load with logic 1 input or logic 0 input, because see, switching means what we are talking like input signal will be switching from high to low state, high to low state, high to low state. Whenever it is switching from high to low state and high to low state, what happens during at one particular amount of time, your particular there will be nothing like input will not be supplied. It means your input will be in between 0 and 1. It will not be like 0 logic 0, or not it will be like logic 1. Between these two phases of the logics which you supply, your transistor comes into this state. That is called as an unloaded inverter. You're not exactly supplying the either logic 1 or logic 0, but in between the switching of this logic 1, see, this is a logic 0 state of the input which you supply over here. This is a logic 1 state. Between these two states, logic 1 and logic 0 state, your transistor will enter into the short circuit condition, and that is called as a short circuit power dissipation, which happens due to current leakage. This unloaded situation means you will not be exactly supplying logic 0 or logic 1. It happens in between these two operations whenever you supply the signal. So this is regarding what is meant by short circuit power dissipation. The next one is called as a total power dissipation. Total power dissipation is nothing else but it's a sum of all the three. So these are the three different types of power dissipation which you have studied up to now. The total power dissipation of a CMOS inverter is expressed as a sum of all the power dissipations. The total power dissipation is equal to the static power dissipation, that is P is equal to V into I, where I is I static, V is a VDD, plus P dynamic, where P dynamic is nothing else but it's C into V square F, where V is the input voltage, that's nothing else but it's a supply voltage which is equal to VDD, and P static, P short circuit power dissipation is nothing else but this is a formula which is used for power dissipation, which depends upon the rising time and also the period of the wave which you are using. The period we are supposed to take care about, talk about the time period of this particular wave, input wave which you supply as an input over here, and also the rise and fall times of this particular input signal. So this is the topic regarding what is meant by power dissipation and how the power dissipation takes place in CMOS inverter and what are the different types of power dissipations in CMOS inverter.